Hello and welcome to the Carl Cummy session that I'm going to be doing today. My name's Mr. Black. I'm from Pengli School. I teach chemistry there, and I'm going to be going through this topic with you today from the Year 10 syllabus, and it's water. Okay, so there's various sections that we'll be looking at on this topic. The first one is where we actually get water from, the drinking water, and how we make it safe to drink. So there's a couple of techniques we're going to look at. So first of all, the sources of water. Well, obviously we're going to be turning our water from sources like this into our drinking water. And our sources can come from, well, obviously reservoirs and lakes. And we can get it from natural lakes. And we can get it from rivers. And another place where we can get water from as well is from what's called an aquifer. And we find these underground. As our demand for water is going up, though, and our supply is dwindling, these aquifers are getting, used up. And we're running out of these aquifers. It's becoming a big problem. Okay, so let's talk about then how we get the water from these kind of sources and make it safe to drink. The water from an aquifer is probably pretty much safe to drink straight away. Obviously, water from a river, lake, reservoir, you need to make it safe. So let's look at the kind of stages involved in that process. So I've got here an overview of the whole process. You can see got various stages. So I'm going to go through each stage in turn. So the first stage we've got in the process is what's called screening. I've seen this as a QER, by the way, this kind of question about this, how you make water safe to drink. And screening is literally where you're going to take out the big material from your water. So, your kind of your litter, your objects like sticks and leaves, okay? We'll also stop creatures, large creatures, from getting through as well into the treatment process. Okay, and then once you've screened the water, it's still going to have the smaller particles in, because you're not going to screen these out, they'll get through the grating. And obviously your water won't be very palatable, you won't want to drink that. And you can see here, basically, what's happening is, though, over time, this muddy water, the sediment's settling out towards the bottom. So this is what we do, we get the water. We let these sediments, these fine particles, kind of sink to the bottom, and so the water will then be clear. And the problem with that process, sedimentation as such, is it's a very slow process. So we speed the process up. And to speed the process up, we have these chemicals called coagulants, and coagulants basically clump these small particles together into bigger clumps, which makes those particles heavier and makes them sink much, much faster to the bottom. All right, so it just speeds up the whole sedimentation process. So this is called coagulation. Once you've coagulated particles, they sink, and that's called sedimentation. Okay, so once we've removed most of those fine particles, what we're going to do then is we're just going to go to this step where we filter now through coal and sand. Okay, and that will make sure that even finer particles that haven't quite sedimented out are removed. Okay, and then once we've done that stage there, we go on to the final step here, which is a really important step, which is where they're adding chlorine to the water. And the reason we're adding chlorine there is it's to kill any harmful microbes that are in the water and that could potentially make you very poorly. Okay, there's lots of nasty waterborne diseases. If your water's not treated properly, you can even have diseases like cholera. If it's not treated medically, will kill quite a lot of the cases that are infected. Okay, so the reason the chlorine is there is to kill your harmful microbes. So next little thing I'm going to talk about here, we're going to talk about water scarcity. If you look at newspaper articles, you'll see water scarcity is becoming quite a big issue, especially with the various factors that are involved in water becoming more scarce, which are worthwhile just being aware of. So there are various reasons that water becomes more scarce. Obviously, climate change. There's less rainfall in certain areas, especially in our sort of African continent, especially in South Africa. They have massive issues with water. You can see that's been marked here in red, showing physical water scarcity. You've also got increased world population, so you've got more people who want to use water for, sanitation and just for drinking and for leisure. And then, of course, you've got industry, which uses a lot of water, especially the clothing industry. So there's lots of reasons why water is becoming more and more scarce. Okay, so where can we get our water from? Well, we'll just go back a slide actually. So I want to just point out, lucky us in Wales, we certainly don't have any water scarcity really to speak of. We're kind of blessed with water, but some of these other countries, especially in the Middle East here, we can see that they are really water scarce. Okay, there's a physical water scarcity. But however, we also notice that some of these countries are surrounded by the sea, and that gives them the opportunity to use the sea as a drinking water source. Obviously, you can't drink salt water, so the last thing you'd want to drink, but we can treat that salt water. We can remove the salt from the water, and a process called desalination. Now, there are various ways desalination can be done, but the WJC just want you to know that we could distill the water off. So you can see here the water's been heated in our round bottom flask. The water eventually boils and evaporates. The water vapor then comes to our condenser, which has got a jacket of cold water around it. And that coldness then causes the water to condense back to a liquid, and we collect our pure water. You'll also notice, by the way, there's a thermometer here. We always position a thermometer near the mouth of the condenser, and this is so we record the boiling point of the liquid that's being collected in the condenser. And you'll notice here it's recording the temperature 100 degrees C, because that's the boiling point of water. Okay, so that's another way we can collect our water through distillation if you've not got much rainfall, these sort of arid regions. So what we've got here now, I've just got a little map for you just to show where desalination plants are. You'll notice one of the areas where we don't have a massive amount of desalination is in actually Africa. And the reason for that is that desalination is a very expensive process. It's a very expensive way of producing water. And so you can see on the map, we've got economic scarcity as well. So these sort of countries, they can't actually afford to treat the drinking water through desalination. So they have an issue with their supply. If we come up to the Middle East, though, obviously it's oil rich. They've got lots of fossil fuels. The reason desalination is it's so expensive is it's energy intensive. Well, if you've got fossil fuels like crude oil, you can provide the energy. And of course, you've got solar power as well. You know, these countries tend to have lots of sunshine, but it involves a lot of money. Okay, there are issues with desalination as well that you should know about. When you desalinate the water, you do end it actually with more salty water that has to be disposed of, and that's usually pumped out to sea where it can actually affect marine ecosystems. And of course, as well, when you're taking in the seawater, you're also bringing in sort of plankton and fish eggs and various other organisms that can pass through the system and obviously destroyed, and that will have obviously impact on ecosystem as well. So, and of course, the other big disadvantage is the cost. You know, it's simply not affordable to many countries. Okay, so that's going to bring us on now. We've kind of looked at how we can get hold of our drinking water. So I'm going to talk about dissolving terms. So these are really, really important that you're familiar with the terms. I'm not going to kind of read them all out for you because you can watch through the PowerPoint a bit later. But a really important term that we're about to kind of talk about here is this word solubility. And solubility basically is a measure of how much of a salt can dissolve in 100 grams of water at a particular temperature, because as you're about to see, solubility, how much of a salt can dissolve, is very, very dependent on temperature. So here, for example, we've got the solubility of sodium chloride. We'll just skip this stage there. So saying it 25 degrees C, the maximum amount you could dissolve in 100 grams of water would be 25.6 grams. If you try to dissolve 25.7 grams, you'd have 0.1 of a gram at the bottom of your beaker that you just simply couldn't dissolve. The only way to dissolve it would be to raise the temperature above 25 degrees C. And that brings us on to what's called a solubility curve. So you can see here we've got a solubility curve for lots and lots of salts. Hopefully you'll recognise all those names. Just a quick recap: naming: sodium nitrate, calcium chloride, lead nitrate, potassium nitrate, sodium chloride, potassium chloride. These ones are potassium chlorate. you'll see that most of these salts, their solubility will sort of increase with temperature. That means you can dissolve more in 100 grams than you could at a lower temperature. There's an exception here. This salt here looks like as you increase temperature, its solubility actually decreases initially, and then the temperature doesn't really affect its solubility at all. Okay, so you need to know how to use these curves, these solubility curves, and what you'd expect to do with them. So a typical question in exam is they may ask you to use the curve to discuss or state what the solubility of a salt would be at a particular temperature. So, for example, you may be asked to find the solubility of salt at 70 degrees C. Pretty simple. You draw a line up to the particular salt you're involved in. So, for example, look at the solubility of potassium nitrate at 70 degrees C. And we can see at 70 degrees C, the solubility of potassium nitrate would be 140 grams per 100 grams of water. You can dissolve a lot of that salt. It's incredibly soluble, potassium nitrate. Just quickly, you can see there, hopefully as well, the solubility of the sodium chloride would it's hardly affected by temperature. It's literally about 20.1 grams per centimetre cubed. It's quite hard. You can't really see the scale there. What's the solubility at 50 degrees C then? So I'll give a little pause. So we come up from 50, hit the line, come across, and we can see it dissolves approximately 80 grams per 100 grams of water. There's something else that you might be asking. It's pretty obvious, but at what temperature is the solubility of potassium nitrate? 100 grams per 100 grams of water. So you'd come up to the 100, come across, hit the line, come down. I'm estimating that at about, I don't know, 57 degrees C. Okay, so another thing that you might be asked to do with a solubility curve, and this is one that people quite often struggle with, and that's to predict the mass of crystals that would form if a saturated solution cools down from one temperature to a lower temperature. Okay, so the thing is about a saturated solution, it can dissolve a certain amount of of salt at that temperature. Can't dissolve anymore. Now, if we allow that solution to cool down to a lower temperature, the solubility drops. It can't dissolve that much salt, and we'll start to see crystals come out of the solution. Crystals that look like this. Okay. So yeah, you might be asked to work out what mass of crystals will form. So if we just go back and see the question I've given you. So it's going from 70 to 40 degrees C, what mass of crystals will form. So I'm just going to pause so you can perhaps have a think yourselves. Okay, and I'm just going to go through that then. So we've already established the solubility at 70 degrees C. Right, so we said that was 140 grams per 100 grams. And now we want to see what the solubility is at a lower temperature of 40 degrees C. Okay, so this 40 degrees C, it can't dissolve 140 grams. It can only dissolve oh, sorry, bear me a second. It can only dissolve about 60 grams. So I'm going to say 60 grams. So the difference between these two values is the mass solid that would form. So that would be 80 grams of salt would form, or solid anyway. Okay. So you've got the solubility at 70 is 140. At the low temperature, going to dissolve 60. The difference between those two values is the mass of solid that would crystallize out. Okay, so we're going to move on now to hard water, and no, we're not talking about ice, which is hard water. We're talking about this kind of hard water. It's water that contains dissolved calcium or magnesium ions. Okay, and you'll know you're in a hard water area because it's very difficult to actually form soap bubbles with soap. Instead, you form this stuff called a scum. I've got some pictures here. So this is what we'd expect in a soft water area with soap. You get lots of soap bubbles, or what we call lava. And then in a hard water area, you'll add soap, and well, it will take quite a lot of soap to actually start to get bubbles. Initially, you'll start to form this scum with the soap and the hard water. Okay, so as I say, you can eventually get bubbles with hard water, but it just takes a lot more soap. And that's actually quite important in one of our slides we're about to move on to, which is where we measure water hardness. Okay, why are some water areas have hard water, whereas areas soft water, but it's to do with the type of rock you've got. Areas of the UK which have limestone and chalk as their main rock will be hard water. So we go down to, for example, the southeast of the UK, Bristol, Bath, particularly known for its hard water. Okay, in Ceredigion, you can see we actually don't have much limestone or chalk or any of those kind of rocks that contain calcium magnesium in them. So we're actually in a soft water area. Okay, oh, bear me a second, that's a pain. Okay, going back to the slide, and I'll try and make sure I don't click on there. So when we come to hard water, there's two types of hard water. Okay, there's what's called temporary hard water, and there's what we call permanent hard water. And the difference between them really is, does boiling remove the hardness? So if you're in a temporary hard water area, if you boil the water, it actually becomes soft water. And if you live in a permanent hard water, literally there's no difference at all. Okay, so water that in a temporary hard water is hard to get a lava with. Once it's boiled, that will then actually form a lava quite easily because we remove the hardness. And I say with the permanent hard water, there's literally no effects on the hardness of the water. And therefore you're just going to need to use as much soap as you did earlier. And that's also useful for us because we can use that for testing hardness, whether it's temporary or permanent, as we'll see. Now, the higher candidates, you need to understand why boiling water, temporary hard water, makes it soft. It's quite difficult, challenging chemistry, and I might, if I get time, go on to it on the actual presentation here, but I'll put it onto the slides anyway if you want to look at that yourselves. So we're going to come on to how we measure hardness now. So the way we actually measure hardness is we take our water sample and we add small amounts of soap each time. Typically, we're going to add 1 ml of soap using this piece of equipment here. It's called a burette. And we'll place a bung onto the conical flask that the water's in with the 1 ml of soap, and we'll shake it up. And if we get bubbles, great. If we don't get bubbles, then we'll add another ml, and we'll shake it again, and hopefully we'll get a lava. But if we don't, we'll keep add another ml. And we keep doing this until we actually do record a lava forming. And then we'll note down what volume of soap is required to form that lava. Okay, so you can see here, I've got some examples of some waters, A to E, and you'll notice that I've got an unboiled value and a boiled value. I'm going to ask you a quick question first one. This catches people out quite a lot. Which sample of these waters, A to E, is actually the hardest water? If you said A, that's what a lot of people say, and it isn't A. The reason I think people say A is because they think, well, look, when it's unboiled, it's hard, and when it's boiled, it's hard, so that must make it the hardest. No. Okay. How hard the water is depends on how much calcium or magnesium is actually dissolved in the water. And the more calcium and magnesium that's dissolved in the water, the more soap you're going to need. And we only look at the unboiled water because we're looking at how hard the water is. We don't care about the boiled value. We're only going to look at the unboiled value. So hopefully now, if you said A, you'll now see that actually it's sample C is the hardest water because it takes the most soap to make it form the lava. However, what you'll notice is once you've boiled it, we only need 1 ml of soap, and what this suggests to us then is that this water here in sample C is the hardest water, but it's only a temporary hardness. If we look at sample A is permanent hardness. We can tell it's permanent hardness because after boiling, there's been no difference in the amount of soap we need to form that lava. So that's the reason why we have the boiled value. It's not to, we don't use that to judge hardness. We use that to judge whether it's temporary or permanent. Sample D, by the way, that suggests to me that's probably distilled water. That's got no calcium or magnesium in it at all. Because you've distilled the water off, you've literally got pure water. And if I looked at sample B, well, I describe sample B as being a mixture of temporary hardness and permanent hardness as well. Okay, and the reason I say that is, after you boil it, it takes less soap to form the lava, but it still needs quite a bit of soap to get the lava. So there must have been some hardness that's not been removed. Okay, I'm just going to talk to you again about this experiment. Just in terms of fair testing, if you are comparing water samples, there are certain things that you'd have to make sure you do to make it a fair test between samples. And one of those would be to use the same volume of water. Okay, you'd have to also use the same type of soap, of course. And also when you're shaking it, you'd have to shake it by the same amount. Otherwise, you wouldn't have a fair test. There is another way that we can measure hardness as well. I thought I put a slide in on there, but what we can do, it might come out later maybe, what we can also do, oh yeah, this is the way you can do it as well. This slide also kind of shows that. We can also do to measure hardness is rather than add the soap one bit at a time, you actually put quite a bit of soap in one go, and then you shake it and see how much lava forms. So you might put, I don't know, 5 mil, and then you measure the height of the lava, and that would give you a judge of who's the hardest water. Obviously, the greater the height of the lava, then obviously the softer the water is. Okay, so now we're just going to talk about the effects of hard water because you need to know this for the exam. So there's positives and there's negatives. So one of the positives of hard water, or disadvantages, sorry, is the fact it forms scum. Okay, so that's a bit of a problem because if you want to actually clean things, you need to have a lava to have the cleaning action, and that makes it more expensive to wash clothes. Okay, so there's a cost issue. You see here on a label from some detergent that if you've live in a hard water area, not quite see where it is now. Yeah, look, hard water area. You need to use 1.5 scoops rather than 1 scoop. I mean, it's not a massive increase in cost, but it's still there. And then there's another issue as well with that, in that you are having to use more of this soap, and that means you're polluting water sources with more detergent. So obviously, the less we use of stuff, the less going to go into the environment, and that's all good. Okay, there are other disadvantages as well. You have to get this line scale that can form on surfaces. It's quite unsightly, and you might have to use cleaning agents like Silit Bang to get rid of that kind of that uh, lime scale. And it can even have quite bad effects as well, not just unsightly. So you can get something called kettle fur. I'll just scroll back so you can see it there. Kettle fur is basically limescale that's formed in a kettle, and it coats the heating element of the kettle with this kind of chalky powder. It's actually calcium carbonate that's forming, or limescale. You see it in this kettle here as well. And even worse than that, it can actually also form on heating elements in boilers. So you can see this is what the boiler heating element should look like, and this is what's happened once limescale's formed on the heating element. This happens particularly in your temporary hard water areas. So if you've got permanent hard water, you don't tend to form the limescale as much on the heating elements as you do in the temporary hard water. So with the permanent hard water. And we can see another, this is a heating tank, hot water tank, and you see it's absolutely caked in this limescale. And that's got a problem in that it actually means that you may have to have the boiler engineer come out to kind of descale the heating element, and it also leads to a loss in efficiency of the boiler as well. So it can actually cause, an increase in your household bills. And you can see there the effect of the lime scale has meant to a loss of efficiency of 40% on our boiler. Okay, so you need to get rid of this lime scale. And a quarter of an inch isn't that much lime scale. Also, it can clog your pipes as well, and obviously that's going to create problems for you. This is called pipe fur. Again, it's just lime scale. And you can see here a really bad example of where a pipe's been completely caked up with this pipe fur or lime scale. Well, there is an advantage to this as well. Pipes do corrode, but this lime scale, the pipe fur, can actually protect the metal from the water. So it does have a bit of a benefit, but not a great one. There are much better benefits, though, to live in a hard water area, and one of those is the health benefits. Okay, so for example, one of the health benefits of living in hard water areas. Obviously, we all know calcium, magnesium is good for your bones. If you live in a soft water area, you're not getting the benefit of calcium, magnesium, and therefore your bones can become more brittle. It's actually a disease called osteoporosis. There's also been shown that if you live in a hard water area, you're less likely to suffer from heart disease or sudden cardiac death. So there's a benefit to health in terms of that. And yeah, it's also actually said to make the water taste nicer and also improves the taste of beer. So one of the things that example will quite like to say about a benefit of hard water areas, it actually makes the water taste nicer and it can actually improve the taste of beer. And in fact, lots of brewing companies make sure that they have their water sourced from a hard water area. Okay. So then the final thing then we're just going to talk about removing hardness of water. I'm not going to spend long on this because it will take far too long to go through it properly. But we already know can move. If it's temporary hard water, we simply need to boil the water. And the reason that this happens is that in temporary hard water, you'll also not only have magnesium or calcium ions dissolved, but you'll also have these hydrogen carbonate ions. The negative charges over here, unfortunately, needs to be next to HCO3. So this is a hydrogen carbonate ion, and these two ions in water together, they don't cause they just exist in water. They're happy being in water together. Okay. And so they'll just exist in your water, and you add the soap, and you won't get the lava because the magnesium's dissolved in the water. But what happens is when we heat water up, the hydrogen carbonate ions actually chemically change, and they become a different ion. They become what's called a carbonate ion. You can see they've lost the hydrogen and got an extra negative charge. Now, this combination of ions, magnesium ions and carbonate ions, not hydrogen carbonate, but carbonate ions, this combination actually form a solid. Okay, and that solid is called magnesium carbonate, and that effectively removes the magnesium and or calcium equally from the water, and that makes the water become soft. This is, by the way, why we get the lime scale building up on our heating elements on our pipes. So when this magnesium carbonate comes out of the water, it forms this lime scale. Okay, and there are other ways to move hardness. Okay, and I'll try and keep this brief as well. One of them is you actually add carbonate ions to the water. So if you've got permanent hard water, that's because you haven't got hydrogen carbonate ions in the water that could turn into carbonate ions. So what we do is we artificially add them. So we add the carbonate ions in what we call bath salts. Bath salts basically are sodium carbonate. And if you go into other Carl and Cymru lessons, you'll see there's lessons about precipitation reactions. That's definitely worth looking at. And basically we have this chemical reaction here. We can see that the calcium sulfate and sodium carbonate form calcium carbonate and sodium chloride, and calcium carbonate, as magnesium carbonate was, is insoluble. And you can see here that we form our solid with the calcium ion now removed from the water. This is what's called the ionic equation as well. So if you're not familiar with these ideas of precipitation reactions and do-si-dos and ionic equations, there are videos that you can find on Carlam which goes through these ideas with you. Okay. And then the final thing we can do for removing water hardness is we use what's called an ion exchange column. You can see here we've got some hard water with its calcium magnesium ions in, and what we do is we pass those ions through silica, a bit like sand, but the sand particles have a negative charge, and attached onto these negatively charged particles, wait a second, we have sodium ions. And this is why we call it an ion exchange column. Now, as I've said here, this technique, it works with all types of hardness, temporary and permanent. And what happens is as we pass our water through the ion exchange column, okay, so I'm showing that there, water passing through, the calcium ions swap with the sodium ions. So they kind of push them off the beads, taking their place. So why we call it ion exchange column. You can see now as my water's going through, what I'm doing is I'm replacing the calcium ions or magnesium ions with sodium ions, and sodium ions don't make your water hard. You won't notice their presence there at all. Okay. What can happen though over time is that your column can become full of calcium magnesium ions. All the sodium ions have been replaced, and now if we try and pass magnesium ions through, there's no one to exchange with. And the exam board want you to know that what you can do is that if you want to, you can recharge the column by simply passing through a very, very concentrated solution of sodium chloride. And that will basically then replace all the calcium magnesium ions back with sodium ions. So you can replace these columns. Okay, so there's more content there. You might want to look up the advantages and disadvantages of those different methods. Usually it involves cost, ease of use. You've also, got things like blended learning that you can go and look at as well. I'm sure they'll cover those concepts. Okay, thank you, and I'll finish the recording there.